Hello and welcome to our nocturnal journey. Get comfortable, close your eyes, and let your mind drift far beyond the boundaries of our planet. Imagine an icy nomad hurtling through the silent darkness of space for billions of years. A rock of ice and dust, a silent witness to the birth of our solar system. What if I told you that deep inside this ancient object we might find the answer to one of humanity's greatest questions? Tonight's sleep lecture is dedicated to Comet 67P / Churyumov-Gerasimenko. We will dive into the incredible history of the Rosetta space mission and explore one of the boldest and most controversial theories in modern astronomy. The theory that hidden within the dark and frigid nucleus of this comet is something alive. Are you ready to find out what truly lies behind the icy veil of this cosmic visitor? Our journey begins right now. To truly understand the depth of this mystery, we must first travel back in time, to 1993, when the European Space Agency green-lit one of the most ambitious missions in the history of space exploration. The mission was named Rosetta, after the famous Rosetta Stone, which helped decipher ancient Egyptian hieroglyphs. Much like its namesake, the spacecraft was tasked with deciphering the secrets of comets, those icy relics left over from the formation of our solar system. The target chosen was Comet 67P, discovered by Soviet astronomers Churyumov and Gerasimenko in 1969. Why this particular comet? Its orbit was convenient, and its size and activity presented immense scientific interest. The mission was unprecedented. For the first time in human history, we were not just going to fly past a comet, but enter its orbit, accompany it on its journey around the Sun, and, most incredibly, land on its surface. 10 years of flight, billions of kilometers traveled, complex gravity assist maneuvers around Earth and Mars, all for the chance to approach the mystery of the origin of life itself. No one suspected then what kind of controversies and astonishing hypotheses this encounter would ignite. So, let's begin our deep dive with the spacecraft itself. Rosetta wasn't merely a camera with thrusters. It was a comprehensive scientific laboratory weighing nearly 3 tons and bristling with 11 sophisticated instruments. Each was designed for a specific task, analyzing the composition of the gas and dust erupting from the comet, mapping its surface across different spectral ranges, measuring its temperature, and studying how it interacted with the solar wind. Just imagine this technological marvel, spending a decade in deep hibernation, conserving every watt of energy during its incredibly long trek through the cold, outer reaches of the solar system. Its reawakening in January of 2014 was a genuine drama. Millions around the globe held their breath, waiting for the signal to confirm the probe was alive. And when it finally arrived, it was hailed as a triumph of human ingenuity. But Rosetta's ultimate secret weapon was its tiny companion, the 100-kilogram Philae lander. It was tasked with achieving the unthinkable, landing on the completely unknown, unpredictable surface of a comet's nucleus. Philae was equipped with a drill to take soil samples, cameras for panoramic images, and a full suite of instruments to analyze the comet's matter directly on location. This was an all-or-nothing bet. A successful landing could give us direct answers about the composition of the solar system's primordial matter. Failure meant losing a once-in-a-lifetime opportunity. The entire journey, the decade of preparation, all led up to this single, crucial moment, the rendezvous with the mysterious Comet 67P. Before we dive into the mission itself, let's take a moment to understand exactly what comets are. In popular culture, they are often referred to as dirty snowballs. While this comparison is generally accurate, it is a huge oversimplification. A comet's nucleus is a complex mix of water ice and frozen gases such as carbon dioxide, methane, and ammonia, alongside solid particles like dust and rock. They are essentially leftover building blocks from the protoplanetary disk that formed the Sun and the planets over 4.5 billion years ago. Comets are, in essence, cosmic time capsules. They hold vital clues about the chemical makeup and physical conditions of that distant era. For most of their existence, they reside in the Oort cloud, a hypothetical spherical region located at the very fringes of the solar system. Out there, in perpetual cold and darkness, they remain almost entirely unchanged. But occasionally a gravitational disturbance from a passing star or another massive object nudges a comet out of its stable orbit and sends it on a long journey toward the center of our system, toward the Sun. That is when things get truly interesting. As it approaches the Sun, the ice on the surface of the nucleus begins to vaporize or, to use the scientific term, sublimate, skipping the liquid phase entirely and turning directly from solid to gas. This process creates the coma around the nucleus, a massive cloud of gas and dust that can swell to hundreds of thousands of kilometers across. Furthermore, the pressure from the solar wind pushes this material away, forming the famous tail, which always points directly away from the Sun and can stretch for millions of kilometers. Comet 67P is one such traveler, and the Rosetta mission was designed to become its first close-up observer. Let's now take a closer look at the star of our story, Comet 67P/Churyumov-Gerasimenko. This object is truly remarkable. When the Rosetta spacecraft finally approached it in the summer of 2014, the very first images stunned scientists. The comet's shape was completely unexpected. It consisted of two distinct lobes connected by a thin neck, which immediately earned it the nickname the rubber duck. The larger part, or the body, measures approximately 4.3 by 4.1 kilometers, while the smaller head is about 2.5 by 2.5 kilometers. This dual structure is likely the result of a very slow collision and merger of two separate objects early in the solar system's history. It wasn't a violent crash, but rather a gentle coalescence. The comet's surface turned out to be incredibly dark, darker than charcoal. It reflects only about 6% of the sunlight that hits it. This extreme darkness is caused by a layer of dust rich in organic compounds. The landscape of the nucleus was stunningly diverse, featuring smooth plains, jagged cliffs, deep depressions, and house-sized boulders. This was not just a lifeless chunk of ice, it was a complex, dynamic world. As it neared the Sun, the comet came alive. Powerful streams of gas and dust, known as jets, erupted from its surface. Some of these jets were predictable, appearing in the same spots when exposed to sunlight. Others were sudden, explosive outbursts. Studying this activity was one of Rosetta's primary objectives, as this process is what forms the coma and the tail, and it holds the key to understanding the comet's internal structure and composition. The mission reached its climax on November 12, 2014. That day, the Philae lander separated from the Rosetta orbiter and began its 7-hour descent to the comet's surface. The operation was comparable in difficulty to hitting a bullet with another bullet over a distance of hundreds of millions of kilometers. Everything proceeded as planned, but at the last moment, the system designed to anchor the craft to the surface, the downward thrusters and harpoons, failed. Gravity on the comet is negligible. Without a reliable anchoring system, the lightweight lander could simply bounce off the surface like a ball, and that is exactly what happened. After touching down at the planned landing site named Agilkia, Philae took 2 gigantic hops. The first jump tossed it a kilometer high, sending it soaring above the comet's surface for nearly 2 hours. The second hop was smaller. Ultimately, the lander became wedged in the shadow of a cliff, in a completely unplanned location which was designated Abydos. This dramatic landing had two serious consequences. First, the precise location of the lander remained unknown for nearly 2 years. It was only found in Rosetta's images shortly before the end of the mission. Second, and most critically, because the final resting place lacked sufficient sunlight, Philae's solar panels couldn't recharge its batteries. The lander managed to operate for only about 60 hours on its main battery charge, sending back priceless data before going into hibernation. Despite all the difficulties, this was an historic moment. For the first time, humanity had successfully achieved a soft landing on a comet's nucleus, and the data Philae managed to collect completely revolutionized many existing theories about the structure of these celestial bodies. So what did we actually learn during the brief 60 hours that Philae was operational and the 2 years Rosetta spent observing from orbit? The discoveries were truly groundbreaking. First, the data analysis revealed that beneath the layer of dust, the comet's surface is incredibly hard, like frozen ice. Philae's drill struggled significantly just to penetrate the ground. Second, and this was a major surprise, the isotopic composition of water on Comet 67P was completely different from that found here on Earth. Water is H2O, but it has heavy variance where one hydrogen atom is replaced by its isotope, deuterium. The ratio of deuterium to regular hydrogen on the comet turned out to be 3 times higher than what we find in Earth's oceans. This discovery dealt a serious blow to the popular hypothesis that comets were the primary deliverers of water to the young Earth. While they might have contributed, it's now believed that the main source of our water was more likely asteroids. But the most striking discovery involved organic materials. Rosetta and Philae's instruments detected an astonishing abundance of complex organic molecules on the comet. These weren't just simple compounds like methane or carbon monoxide. 16 different organic compounds were identified, including alcohols, amines, and carbonyls. 4 of these, methyl, isocyanate, acetone, propionaldehyde, and acetamide, had never been detected on a comet before. These are complex molecules that serve as crucial building blocks for even more intricate structures, such as amino acids and sugars, the very foundations of life as we know it. And this brings us to the most compelling, most intriguing twist in our narrative. Against the backdrop of groundbreaking yet purely scientific discoveries, an announcement was made that sent shockwaves through both the scientific community and the general public. 2 highly respected scientists, astronomer Chandra Wickramasinghe of the Buckingham Centre for Astrobiology and his colleague Max Wallace from Cardiff University, stepped forward with a truly sensational hypothesis. They claimed that the distinctive surface features and behavior of Comet 67P/Churyumov-Gerasimenko were best explained by the presence of life itself. Not just complex organic molecules, but a vibrant, active microbial ecosystem thriving beneath the comet's icy surface. In their view, the dark color of the comet's nucleus wasn't simply carbonaceous dust, it was the residue of microbial life. They hypothesized that beneath this thin layer of dust lurked pockets of liquid water, or a water ice slush, providing a habitat for these organisms. Allegedly, these microbes utilized antifreeze salts, allowing them to remain active even in the brutal cold. The jets erupting from the surface, they argued, were not merely sublimating ice, but rather gas emissions produced by these very microorganisms, blasting their way through the crust. The announcement landed like a bombshell. Could a mission designed purely to search for the building blocks of life have accidentally stumbled upon life itself? The idea seemed fantastic, almost science fiction, but its proponents were not crackpots or amateurs. They were established scientists, and that lent their theory undeniable weight. Let's take a closer look at the key arguments put forward by the hypothesis's proponents. Their theory rested on several crucial observations made by the Rosetta mission. The first argument centered on the comet's surface, which, as previously noted, is extremely dark and rich in organic compounds. Wickramasinghe suggested this dark material could be formed when microbial colonies are exposed to solar radiation, much like certain terrestrial bacteria produce protective pigments. The second piece of evidence was the presence of smooth, ice-covered regions on the comet, which looked remarkably like frozen lakes or ponds. The researchers hypothesized that these were actually the very subsurface water reservoirs that periodically melt and then refreeze. The third argument involved the detection of highly complex organic molecules. Proponents argued that such chemical diversity was too complex to be explained solely by abiogenic or non-biological chemical processes. Instead, they suggested it strongly resembled the metabolic byproducts of living organisms. They even went so far as to point out specific surface features in the images that, to their eye, resembled fossilized microbial remains. For instance, they highlighted large boulders covered in strange fissure patterns, and flat-bottomed craters they interpreted as possibly being dried-up lake beds. According to the proponents, the totality of this data painted a singular picture. Comet 67P is not a dead chunk of rock, but a living, breathing world teeming with extremophile microbes. They drew parallels to ecosystems found in Earth's own Arctic ice, where life has found ways to survive even the most hostile environments. The notion of life thriving on a comet is undeniably exciting, capturing our imagination. But what is the official scientific consensus on this hypothesis? Unsurprisingly, the vast majority of scientists involved in the Rosetta mission, along with astrobiologists globally, approached this hypothesis with profound skepticism. While acknowledging the observations were interesting, they consistently maintained that for every piece of purported evidence, there exists a far simpler and more plausible non-biological explanation. Let's dive into their counter-arguments, starting with the comet's dark surface color. True, the surface is rich in organic material, but this doesn't automatically imply biological activity. Complex hydrocarbon compounds, known as tholins, form naturally in space when simple molecules like methane and ethane are bombarded by ultraviolet radiation. Tholins possess a distinctive dark reddish-brown hue, which perfectly accounts for the blackness of the cometary nucleus without needing to invoke biology. Next up, the so-called frozen lakes and other unique geological features. ESA scientists explain these through complex cycles of sublimation and recondensation. As one section of the comet is heated by the sun, ice sublimates. It turns directly from solid to gas. This resulting vapor then refreezes onto colder, shaded areas, creating those smooth, often expansive, icy sheets. Finally, the active jets are purely geological phenomena. Pressure builds up as gases accumulate beneath the surface, eventually causing a breakthrough in the overlying dust layer. This is a fundamentally physical process that requires absolutely no microbial intervention. Let's address the most critical point, the presence of complex organic molecules. Indeed, their detection was arguably the mission's single most important result. But does their existence automatically imply the presence of life? Not necessarily. Modern astrochemistry has demonstrated that complex organic compounds not only can form but do form in vast quantities throughout the cosmos. The molecular clouds from which stars and planets emerge are veritable factories for organic synthesis. Chemical reactions occurring on the surface of icy dust grains, triggered by cosmic rays and ultraviolet light, are capable of building highly complex molecules from the simplest raw materials. Consequently, the detection of glycine, alcohols, and other such compounds on a comet is not evidence of life on the comet itself. Instead, it confirms that the building blocks of life were abundant in the primordial environment from which our Earth was synthesized. Comets and asteroids impacting the young Earth likely delivered these crucial ingredients, providing the necessary catalyst for life to emerge on our planet. This theory, known as panspermia, or in its milder form, exogenesis, is receiving ever-increasing confirmation, and the findings of the Rosetta mission are a powerful argument in its favor. It turns out the comet isn't the cradle of life, but rather its cosmic delivery service, dropping off the necessary ingredients exactly where they were needed. As for the structures initially mistaken for fossils by proponents of the hypothesis, they turned out to be simple geological formations, a trick of light and shadow, or, as scientists often call it, pareidolia, the innate tendency to perceive familiar patterns in random visual stimuli. So was the whole story about some creature lurking in the heart of the comet nothing more than a fiction? From the perspective of strict scientific methodology, the answer is yes. Not one piece of direct, undeniable evidence for life on Comet 67P has ever been presented. All the observations that the hypothesis relied upon have much simpler and more logical physical and chemical explanations. Science operates based on Occam's razor. The simplest explanation is usually the best, and you shouldn't introduce complex entities unnecessarily. And the microbial life hypothesis is exactly that, a complex entity. Its existence requires highly specific conditions, sustained liquid water beneath the surface for extended periods, shielding from harsh cosmic radiation, and a viable energy source. While theoretically some of these conditions might be met at certain points in the comet's orbit when it swings close to the Sun, there is no evidence that they exist stably or persistently. Nevertheless, this story holds great importance. It serves as a perfect demonstration of the scientific process itself. A bold, beautiful hypothesis is first proposed. It is then subjected to comprehensive criticism and rigorous testing. If it withstands the scrutiny of facts and experiments, it can be promoted to a theory. If it fails, it is either discarded or modified. In this specific case, the hypothesis of life on the comet did not pass the test. But it did force scientists to meticulously re-examine the existing data and push the boundaries of what they considered possible. Crucially, it drew immense public attention to the Rosetta mission and to the field of astrobiology as a whole. Let's turn our attention back to the mission's actual discoveries, findings that are no less exciting than any hypothetical scenario. One of the most significant achievements was the detailed analysis of the coma, the gaseous and dusty cloud surrounding the comet's nucleus. Rosetta's instruments successfully captured and analyzed the molecules spewing directly from the surface. This is how, in 2016, a discovery was made that many considered just as sensational as the possibility of finding hypothetical life. The amino acid glycine was detected within the comet's coma. Amino acids are the fundamental building blocks used to construct proteins, the basis of all terrestrial life. Glycine is the simplest amino acid known. While traces of glycine had previously been found in samples of cometary material returned by NASA's Stardust mission, those findings were always marred by the suspicion of terrestrial contamination. Rosetta, however, took its measurements directly at the comet, eliminating any potential for error. This marked the first undisputed detection of an amino acid within a cometary coma. But the discoveries didn't stop there. Alongside glycine, the mission also identified phosphorus, another crucial element for life. Phosphorus is a vital component of DNA, RNA, and cellular membranes. Thus, on a single celestial body, scientists found both the literal building blocks for proteins and the essential element required for the genetic code and cellular structure. This finding provided the strongest confirmation yet that comets truly played a decisive role in the genesis of life on Earth, delivering not just water, but a complete set of necessary organic precursors. Beyond the organic molecules, Rosetta uncovered another incredible secret, this one about the comet's gases. Molecular oxygen, O2, was detected in the comet's atmosphere. This was a total surprise. Oxygen is extremely reactive. It readily combines with other elements, particularly hydrogen, to form water. Scientists had long assumed that there couldn't be any free oxygen in the pristine material dating back to the solar system's formation. Yet 67P contained a surprising amount of it. It ranked as the fourth most abundant gas, right after water vapor, carbon monoxide, and carbon dioxide. This finding immediately forced scientists to completely rethink their models for the formation of comets and the entire solar system. The existence of molecular oxygen suggests it must have been locked inside the comet when it first aggregated 4.5 billion years ago. This, in turn, implies that the conditions within the protoplanetary disk were fundamentally different from previous assumptions. It is possible that the icy material forming the comets aggregated at extremely low temperatures within a very quiet environment where the oxygen simply couldn't react with the hydrogen. Therefore, Comet 67P not only shed light on the origins of life, but also provided a fresh perspective on the processes that gave birth to the planets themselves. Every new molecule discovered in its tail is a fundamental letter in the universe's oldest alphabet, an alphabet we are only just beginning to decipher. The geological observations were just as fascinating. Rosetta spent over 2 years orbiting the comet, monitoring its transformation as it approached the Sun and then receded. These observations provided the first detailed look at how a comet truly works. It turned out that its surface is constantly changing, experiencing genuine landslides. In August 2015, shortly after the comet reached perihelion, the point closest to the Sun in its orbit, scientists captured images showing a massive collapse. An entire cliff face, 70 meters high and 100 meters wide, had crumbled. This event exposed the comet's inner layers, revealing bright blue ice previously hidden beneath the dark dust crust. This exposed ice was found to be 6 times brighter than the average cometary surface. Such events demonstrate that erosion on comets isn't a slow, gradual process. Rather, it's driven by a series of abrupt, catastrophic occurrences. In addition to landslides, Rosetta observed the formation of features dubbed goosebumps, small, dome-shaped structures on the surface that appeared and vanished throughout the cometary day. This is likely the result of subsurface ice sublimating. All these dynamic processes transformed our understanding of the comet from a static object into a vibrant, changing landscape, providing geologists with invaluable information about the physics of icy bodies in space. Let's circle back to the theory of panspermia, a concept that the Rosetta data significantly bolstered. The notion that life can travel between planets or even star systems isn't new. It was actually proposed as far back as the 19th century. According to this hypothesis, microorganisms can be encased inside asteroids or comets. If these bodies are knocked out of their parent system, say by a collision with another object, they embark on a long interstellar journey. While in a state of deep suspended animation, they can survive millions of years in the vacuum of space, shielded from radiation and extreme cold by thick layers of rock and ice. If such an arc happens to enter the gravitational field of another planetary system and crashes onto a world with suitable conditions, these microbes could reactivate and potentially spark a new evolutionary lineage. For a long time, panspermia was dismissed as mere science fiction. Yet with every new discovery, it seems increasingly plausible. We already know that certain terrestrial microorganisms, the so-called extremophiles, can survive truly incredible conditions: extreme temperatures, high pressure, vacuum environments, and high doses of radiation. Experiments conducted aboard the International Space Station have demonstrated that some bacterial spores can survive in the harsh environment of open space for years. The discovery of organic molecules on comets and asteroids further proves that the essential building blocks of life are widespread throughout the universe. In summary, while Rosetta did not discover life itself, the mission provided compelling evidence that comets are indeed ideal transport vehicles for life's essential ingredients. While the hypothesis of life existing on Comet 67P has been debunked, it forces us to confront a much broader question. Where else in the solar system could life possibly exist? These days, the leading candidates aren't comets at all, but rather the moons orbiting the giant planets. Take Jupiter's moon, Europa, for example. Scientists theorize that beneath its miles-thick icy shell lies a global ocean of liquid, salty water. This ocean is likely warmed by Jupiter's immense tidal forces, and its seabed may harbor hydrothermal vents, much like those found here on Earth. On our planet, life thrives around these deep-sea vents, completely independent of sunlight. A similar scenario might be playing out on Saturn's moon, Enceladus. The Cassini spacecraft famously flew directly through geysers, blasting out of cracks in its icy surface, detecting water, organic molecules, and particles of silicate dust. This combination strongly suggests a subsurface ocean that is actively contacting a rocky core. Then there is Saturn's largest moon, Titan. While the conditions there are drastically different from Earth's, they might still support exotic forms of life. Titan is home to rivers and lakes, but they are composed not of water, but of liquid methane and ethane. It is possible that life there is based on methane rather than the familiar water-based chemistry we know. These fascinating worlds are all waiting for exploration, and the lessons learned from the Rosetta mission will be invaluable as we plan future expeditions to these icy moons in search of the ultimate answer. The Rosetta mission came to its dramatic conclusion on September 30th, 2016. As the comet moved farther and farther away from the Sun, the probe's solar panels could no longer generate sufficient power. The decision was made to bring the mission to a close with a spectacular finale that mirrored its ambitious journey. Rosetta was then guided toward a slow, controlled impact with the comet's surface. During its final hours, the probe transmitted unique images and data captured from a record-breaking proximity. It showed us the comet's surface from an altitude of only a few dozen meters, providing detail that had previously been unimaginable. The final signal from Rosetta was received when the craft was just 20 meters above the surface. It was the end of a great odyssey. The craft that had accompanied the comet for so long was finally reunited with it forever. Rosetta, along with its tiny companion Philae, now rests permanently on the surface of this ancient world, continuing their endless journey through the solar system, but their legacy remains with us. Scientists will analyze the tens of terabytes of data they transmitted for many years to come, leading to new discoveries. Rosetta didn't just show us what a comet looks like, it fundamentally changed our understanding of planet formation and the origin of water and organic molecules here on Earth. While it didn't find living creatures, it brought us closer to unlocking the mystery of life's own genesis. It transformed a distant, faint point in the sky into a complex, dynamic, and beautiful new world. So, what can we finally conclude about the entities supposedly hiding within the nucleus of Comet 67P? We can confidently say that there is no compelling evidence whatsoever of its existence. It was a beautiful and bold hypothesis, but one that failed to find scientific validation. Nevertheless, it became a significant cultural phenomenon, demonstrating the depth of our interest in finding extraterrestrial life and just how ready we are to believe in a miracle. The real miracle discovered by the Rosetta mission, however, turned out to be no less fascinating. The miracle is that this lump of dirty ice, hurtling through the vacuum of space, contains the very same molecules that make up you and me. Glycine, phosphorus, complex hydrocarbons, all the essential elements for the genesis of life, were forged in the hearts of stars and scattered throughout the universe. Comets, acting as ancient cosmic sowers, delivered these seeds across nascent planets, and on one of those planets, our own Earth, those seeds fell onto fertile ground. They combined within warm oceans, formed the first self-replicating molecules, and initiated the grand process of evolution. This process ultimately led to the emergence of a consciousness capable of looking back into space and finding its distant chemical ancestors. The story of Comet 67P is not about the search for aliens. It is a story about finding ourselves, about understanding our deepest cosmic roots. And it tells us that we don't just live in the universe. We are the universe, attempting to know itself. Let's take a moment to transport ourselves back to the comet's surface. Try to visualize this incredible world. Gravity is almost non-existent. A slight push could send you drifting straight into space. The sky is an absolute void, pitch black, where brilliant, unwavering stars hang motionless. And the sun, a colossal, dazzling source of light, doesn't appear as a disk here, but more like the most brilliant pinpoint imaginable. Surface temperatures swing wildly, from a scorching plus 50 degrees Celsius on the sunlit side to a chilling minus 150 in the shade. What's underfoot isn't rock or sand as we know it, but a loose mixture of dust and ice, highly porous and incredibly light. In fact, the comet's nucleus is less dense than water. If you could find an ocean big enough, the entire thing would float like a giant piece of pumice. Yet despite this seemingly dead silence, activity is constant. Somewhere beneath the surface, ice is heating up, pressure is building, and suddenly a jet of gas and dust erupts from a fissure with a hiss, carrying ancient material out into space. Massive boulders slowly shift and roll down the slopes, driven by this weak yet persistent activity. It is a world that is simultaneously dead and fiercely alive with its own non-biological existence. Thanks to the Rosetta mission, we were able to see this world with our own eyes, to explore its valleys and mountains and finally touch its mysteries. This is an invaluable experience, cemented forever in human history as the first tangible step toward understanding these enigmatic cosmic wanderers. It's worth noting that the comet's distinctive, rubber duck-like shape provided scientists with significant clues. Analysis of the neck structure, which joins the two lobes, showed that it is layered almost like an onion. This strongly supported the theory that the comet was formed from two separate objects, but the exact mechanism remained unclear. Scientists considered two main hypotheses. The first possibility was a very slow-motion collision early in the solar system's history. The second was that it started as a single object, whose unusual shape was later carved out by uneven erosion, specifically the sublimation of ice. The Rosetta mission ultimately provided the answer. By analyzing the comet's gravitational field and internal structure, researchers found that the internal layers in the two lobes were oriented completely independently. This conclusively proved they formed separately and only merged later. Crucially, the impact was incredibly gentle, moving at roughly walking speed, meaning the two bodies didn't shatter, they simply stuck together. This discovery is profoundly important because it reveals the process by which planetesimals, the building blocks of planets, initially formed. The process wasn't as chaotic and destructive as previously theorized. Instead, it was a slow, gradual accumulation, a gentle clumping of smaller objects that progressively grew into larger bodies. Comet 67P is essentially a perfect visual example of this primordial accretion, frozen solid in time. Let's take a slight break from the pure science for a moment and discuss the cultural significance of the Rosetta mission. The European Space Agency did an absolutely brilliant job of popularizing the mission. They created moving, animated shorts about the adventures of Rosetta and Philae, which totally humanized the probes and turned them into the heroes of a real-life space saga. They even set up social media accounts in the probes' names, allowing them to chat with each other and with their followers. This meant that millions of people worldwide followed the mission not as some dry scientific endeavor, but as a gripping drama. The moment Rosetta woke up, the dramatic landing of Philae, its brief operational window before going dormant, and then the unexpected short second awakening months later. All these events felt like milestones in the lives of close friends. This communication strategy proved to be phenomenally successful. It proved that science can be interesting, emotionally engaging, and accessible to everyone. The Rosetta mission inspired an entire generation of young people to pursue careers in space exploration, engineering, and science. It demonstrated that exploring the universe isn't just about collecting data. It's a grand adventure of the human spirit, full of hope, hardship, and ultimately triumph. And that perhaps is a legacy just as crucial as all the scientific breakthroughs the mission delivered. Another fascinating aspect concerning Comet 67P is its so-called song. One of the instruments aboard the Rosetta spacecraft was specifically designed to study the comet's magnetic field. It detected strange oscillations in this field, occurring at extremely low frequencies, between 40 and 50 millihertz, far below the threshold of human hearing. Scientists converted these oscillations into the audible range, allowing the world to hear the mysterious hum or singing of the comet. This resulting sound, resembling strange clicks and crackles, immediately sparked intense speculation. Some quickly claimed these were signals from hypothetical extraterrestrial beings. But the scientific explanation, as is often the case, turned out to be more prosaic, yet no less intriguing. Most likely, these fluctuations are created by the ionization process of molecules escaping the comet's surface, driven by the solar wind. In essence, it is the sound of the cometary atmosphere interacting with the stream of charged particles emanating from the sun. Nevertheless, the ability to actually hear the comet made a profound impression on people. It provided another way to truly feel this distant world, making it more real and tangible. This is the sound of processes that occurred long before human existence and will continue for billions of years to come. It is the music of the solar system itself, and Rosetta allowed us to hear its performance. What lessons can we draw from the Life on a Comet saga? The main takeaway is the absolute necessity of critical thinking. In an age where information spreads instantly, it's incredibly easy to fall for sensational headlines. The story sounded too good to be true. Scientists found aliens, but that's simply not how science operates. Every extraordinary claim must be backed by irrefutable evidence, proof that can be tested, verified, and replicated by independent researchers. In the case of Comet 67P, that evidence just wasn't there. There were only data interpretations that had alternative, far simpler explanations. Now, this doesn't mean we should stop searching for life in space. Quite the opposite. We absolutely must continue. But we must approach this search methodically, cautiously, and without allowing wishful thinking to cloud our judgment. The search for extraterrestrial life is a marathon, not a sprint. And even if we never find little green men, the search process itself enriches our understanding of the universe and our own place within it. Every mission, like Rosetta, even if it doesn't confirm alien life, still finds something equally important: fragments of the puzzle of our own origins. Let's dive into yet another feature that makes comets such fascinating subjects for study: their crucial role in delivering not just organic compounds, but also noble gases to Earth. Noble gases like argon, krypton, and xenon are highly inert. They hardly react with anything chemically. Their isotopic composition in Earth's atmosphere acts as a unique fingerprint, one that reveals the materials that originally formed our planet. But here's the interesting part. The noble gas makeup of our atmosphere doesn't exactly match what we find in the Sun or in meteorites, the bodies typically considered the primary building blocks of the solar system. Specifically, there was a noticeable deficit, particularly of xenon. The Rosetta mission was the first to successfully measure the noble gas composition directly on a comet. What they found was that it perfectly complements those missing atmospheric components. By mixing this cometary cocktail with the asteroidal material in the correct proportion, scientists can recreate a composition extremely close to that of the Earth's atmosphere. This provides powerful evidence that our planet wasn't formed from a single source, but rather from a blend of different bodies arriving from various regions of the young solar system. The comets, having journeyed in from the cold, distant edges of the system, brought with them not only frozen water and organics, but also the volatile noble gases that helped forge the very air we breathe today. Let's circle back to the search for life. It's crucial to grasp just how extreme the conditions on a comet truly are. Beyond the intense cold and the vacuum of space, the primary threat to any life form is cosmic radiation. Unlike Earth, a comet lacks a dense atmosphere or a magnetic field to shield it from the relentless flow of high-energy particles streaming from the Sun and deep space. This radiation is devastating to complex organic molecules, especially DNA. Any microorganisms on or near the surface would be sterilized in a very short period. Theoretically, life could exist some distance beneath the surface, where a protective layer of ice and dust might offer a buffer. But that leads to a different problem: the complete lack of an energy source. On Earth, life utilizes either solar energy via photosynthesis or chemical energy via chemosynthesis, like we see near hydrothermal vents. On a comet, sunlight cannot penetrate deep, and chemical reactions needed to support metabolism proceed extremely slowly, if at all, in conditions of perpetual deep freeze. All these factors combined make the existence of an active microbial ecosystem on a comet highly improbable. Perhaps frozen, dormant spores could be preserved there, but thriving, flourishing life is purely the stuff of science fiction. The Rosetta mission was a truly global endeavor, bringing together scientists and engineers from dozens of countries. It is a prime example of what humanity can achieve when we unite our efforts to solve grand challenges. The total cost of the mission was approximately 1.4 billion euros. That sounds like a massive sum, but when you break it down across all citizens of the participating nations over the project's 20-year lifespan, the annual cost per person is roughly equivalent to a single cup of coffee. For this investment, we gained fundamental knowledge about our origins, inspired millions globally, and delivered significant technological breakthroughs. Projects like these drive civilization forward. They don't just answer our questions, they pose new, even more ambitious goals. The next logical step in cometary research could be a mission to deliver core samples back to Earth. Imagine this. Instead of just analyzing the material remotely, we could study it in the world's most advanced laboratories, utilizing technologies too complex or massive to send into space. Such a mission would allow us to delve even deeper into the secrets of these icy worlds, potentially revealing more complex organic molecules that Rosetta simply wasn't equipped to detect. Let's take a moment to imagine what would have happened if the hypothesis of life on a comet had actually been confirmed. If the Philae lander, using its drill, had pulled out not just organic compounds from beneath the ice, but actual living microorganisms. That would have been, without exaggeration, the greatest discovery in human history. It would have meant that life isn't a unique phenomenon that originated solely on Earth, but rather a widespread common occurrence throughout the universe. It would have shown us that life can emerge and persist even in the most improbable and harshest environments. This would have changed everything: our philosophy, our religion, our understanding of ourselves. We would have finally known we weren't alone. And even if that life were nothing more than primitive microbes, it would have been proof of the fundamental principle itself. Unfortunately, or perhaps fortunately, that discovery didn't happen. Comet 67P turned out to be lifeless, but that certainly doesn't mean life doesn't exist elsewhere. The search continues. Every new mission, every powerful new telescope brings us closer to the moment when we might finally be able to say with confidence, we are not alone. For now, we can only look up at the stars and dream, comforted by the knowledge that we are made of the very same star stuff as those distant worlds. Interestingly, the story of Rosetta and Philae is laden with symbolic meaning. The name Rosetta is a direct reference to the stone that helped us unlock Egyptian hieroglyphs. The spacecraft, in turn, was meant to decipher the language of comets. The Philae lander was named after an island in the Nile, the location where an obelisk, also covered in hieroglyphs, was moved, an obelisk that provided crucial context for deciphering the Rosetta stone. In essence, Philae was designed to be the physical key, allowing Rosetta to read a message delivered directly from the deep past. Even the chosen landing site, Agilkia, continues this tradition. It's the name of the island where the temples from Philae were relocated before the original island was submerged during the construction of the Aswan Dam. The entire mission was steeped in these beautiful historical parallels. It was conceived not merely as a flight to a comet, but as a grand act of decipherment, an attempt to read the book of our world's origins, written in the ancient language of ice and dust. And even though we haven't yet managed to read every single page, we did find the dictionary, uncovering the molecular letters on the comet, the very building blocks from which the word life is written. This poetic legacy of the mission is arguably just as important as its hard scientific results. It reminds us that science isn't just about formulas and charts, but a great human story of discovery. Let's go back once more to the very beginning, to the comet's discoverers. In 1969, Klim Churyumov and Svetlana-Gerasimenko were working at the Alma-Ata Observatory. They were studying photographic plates of a different comet when Svetlana-Gerasimenko noticed another previously unknown object right on the edge of one plate. At first, they thought it was just a defect in the emulsion. But after checking other images, they realized they had found a new comet. At the time, they couldn't possibly imagine that 45 years later, the most complex spacecraft built by thousands of people would be sent to this tiny, faint object, and that the name of their comet would be known worldwide. Sadly, Klim Churyumov passed away in October 2016, just a few weeks before the mission was fully concluded, but he was able to witness all of Rosetta's major triumphs. This story is a perfect illustration of how fundamental science, simple curiosity, and observing the sky can lead to truly world-changing results. It all starts with one person looking through a telescope and noticing something unusual. And it ends with an international mission attempting to answer the deepest questions of existence. That is the very essence of scientific progress. Ultimately, Comet 67P/Churyumov-Gerasimenko proved to be a real cosmic treasure trove. While it didn't gift us alien beings, it delivered something far more profound. It confirmed that our young solar system was, in fact, a colossal chemical reactor, churning out complex organic molecules in abundance, the very building blocks of life itself. It demonstrated that comets were likely the primary delivery system, bringing both these vital molecules and water to young planets, including Earth. This mission has forced us to fundamentally revise our models for the formation of planets and their atmospheres. Furthermore, the mission showcased the incredible sophistication of human technology, our capacity to send autonomous laboratories across billions of kilometers and execute a successful landing on a tiny, rapidly moving cosmic body. The Rosetta mission did not close the book on the origin of life. Instead, it penned a thrilling new chapter and left behind a host of intriguing questions for future generations of scientists. And the central conclusion we can draw as we reflect on this profound story is simple. We are all children of the stars and the comets. Our very bodies are composed of atoms that were once components of these icy wanderers, much like Comet 67P. This singular realization connects us to the universe far more profoundly than any fantastical tale of hidden life. Let's consider another fascinating fact. The comet's surface isn't just diverse, it's incredibly dynamic. One of the most astonishing phenomena recorded by Rosetta were the so-called singular outbursts. Occasionally, without any apparent warning, an extremely powerful jet of gas and dust would erupt from a deep depression on the surface. One such outburst increased the brightness of the comet's coma sixfold, expelling about 180 tons of material into space. Scientists hypothesize this might be caused by the collapse of subsurface cavities where high-pressure gas had accumulated. It's almost like a dam breaking. These events demonstrate just how hazardous and unpredictable a comet's surface can be for future missions, or even for hypothetical colonists, should humanity ever decide to utilize comets as a source of water and resources. Studying this geological activity is key to understanding not only the comet's past, but also the future of space exploration. Every fissure, every landslide on Comet 67P is a lesson we must learn before taking our next steps into the solar system. This tiny world has taught us countless lessons about humility in the face of natural forces and about the greatness of the human mind, which is capable of understanding them. And so our long voyage to Comet 67P is finally drawing to a close. We have journeyed billions of kilometers alongside Rosetta, witnessing its triumphant arrival in deep space. We relived the dramatic landing of Philae and, alongside the world's scientists, sifted through the invaluable data it managed to transmit. We explored that bold, intriguing theory about life hiding beneath the ice, and we learned why the scientific community ultimately dismissed it. But we discovered that reality itself was every bit as astonishing as any fiction. There were no creatures found in the comet's icy heart. Instead, we uncovered something far more fundamental, the very blueprint of our own chemical roots. We discovered amino acids and phosphorus, the essential building blocks of life itself, proof that we are inextricably linked to the cosmos. The comet was not the cradle of life, but rather its cosmic delivery service, dropping off this priceless cargo onto the nascent Earth billions of years ago. The Rosetta mission is truly a magnificent story of human curiosity, genius, and our timeless need to understand our place in the wider universe. Thank you for spending this time with me traveling deep into the cosmos. I truly hope that this journey has helped your mind relax and prepare for a deep, restful sleep. If you enjoyed this cosmic deep dive, please consider liking this episode and subscribing to the channel for more space and science-based sleep stories. Now, as you drift off to sleep, let me leave you with one final question to ponder. If the foundational building blocks of life are so prevalent throughout the universe, how likely is it that somewhere else they have assembled into something truly intelligent? Feel free to share your thoughts in the comments when you wake up. But for now, sweet dreams to you, and may your slumber be filled with a clear, starry night sky. Good night.